It's wonderful to be here. I've always I've never been in Arizona before, and this has been I go to a lot of statistics meetings, and I can tell you this is a lot more fun than my statistics meetings. Probably shouldn't say that because people don't like to take stat courses, but anyway, I'm going to talk about batting average, and of course, batting average. Say, oh, who cares about batting average? Well, it's actually a pretty old prediction problem, and so it's interesting. But really, there's a lot more to a batting average. So I think once you dissect it, then you find out that really it's actually more than one dimension. It's many dimensions. So, okay, so this is the basic problem, and we're probably all familiar with this problem. You have a guy who's this is midseason. He's got a 300 or higher batting average. And last season, there were 38 players in that category, roughly, one or two players a team. And so what you want to do is you want to predict their final season batting average. And this is actually a very old problem. In fact, I was a graduate student a long time ago, and my advisor said, well, you should read these papers by Effron and Morris. And Effron and Morris were talking about shrinkage estimation, and they wanted to illustrate their methods on a really practical problem. And so they said, well, why don't we look at baseball data? And now back in the 70s, it was a different time before computers. And where did you find baseball data? The Sunday paper. So the Sunday paper, you would see like a big tables of batting averages. So what they did is they pulled data for 1 month, and they picked out players who had exactly 45 at-bats, and they wanted to predict their final season batting averages. So this has been in fact, there's a famous data set, and this example is still being used in textbooks, to introduce Bayesian, so they use it to illustrate Bayesian methods. So anyway, so that's the basic problem. Now, let's move on here. Okay, so here are two players that fit in this category last season, Norioki and Joey Butler. They both were 300 batting averages or higher mid-season. And so they're obviously, we'll talk about these two hitters. They actually had very different patterns of hitting. But if you're just talking about batting average, they're just lumped together as good hitters. Okay. Now, this is a typical thing. We know that batting averages will tend to shrink or regress to the mean. So there's a standard way of doing this, and that's what Effron and Morris talked about. And so we can call this a random effects model. We can call it a mixed models or, a multi-level. And so here's an example. I fit this model, and I get these parameters, estimated parameters. Now, let me explain what these parameters mean in a second. Essentially, here's a very simple example of using this procedure. You have a guy who has 250 at-bats, and he gets 80 hits. Okay, so he's got a 320 batting average. And you want to predict, basically what you're doing is predicting his talent, his baseball talent or ability to hit. So what you essentially do is you just add that data with a bunch of average players. And so you take, 483 average players, and you just pull that or combine that with your data. So you just take, you take 80 hits, you add, 483 players who have an average batting average, and you just change the denominator, and you get 283. So basically, even though he batted, 320 for the half season, you think his batting ability is more like 280. And this is a traditional method, and so we do this all the time. Now, okay, we know we can do this, but actually, there's more going on here because when you talk about hitting for average, okay, what does that mean? Well, first, you can't strike out. Okay, basically, you have to get the ball in play. So the first thing you have to do is not strike out, and if you do not strike out, then you got to get a hit and a ball in play. So really, a batting average is a product of two numbers. And the first number is 1 minus the strikeout rate. And the second number is hits and balls in play. Okay, so we'll include home runs for now in that thing. So really, at the very least, a batting average, there really are two components. And so really, now the question is, we'll look at this in a second, but why this matters. But so there's more going on. When you talk about hitting for average, there's actually what you're saying is that he's not striking out, and he's also getting balls getting hits and balls in play. So you get this basic representation. Okay, so we have to think about batting ability as being first as not striking out and also getting hits. And so one way you can visualize a batting average is you plot those two numbers. You plot 1 minus, we saw that it was a product of these two numbers, so you just plot the 1 minus the strikeout rate against the batting average and balls in play for each hitter. Okay, so we're just going to look at these two numbers for all the players last season who had a 300 batting average at midseason. So here's a graph, and if you look at the graph, you'll see now what I have here. So the horizontal is 1 minus the strikeout rate. The vertical is the hit and play rate. Each dot corresponds to a player, and I've drawn some contours, and the contours correspond to constant values of batting average. So since we're looking at the guys who batted 300 or higher, they're all above that line. Now, the next contour is 350, so I guess there are a few players that were batting 350 at midseason. Okay, now you look at that picture, there are different kinds of hitters represented. So down here, we got the low strikeout guys. Okay, these are the guys who really don't strike out, they get their bat on the ball. Now, their hit and play rate is pretty small, but they compensate that by a low strikeout rate. So when we're thinking about guys like that, we're thinking about guys like Aoki, we're thinking about Michael Brantley, Buster Posey. These are all guys who have basically didn't strike out very much. But they still, because of that, they were able to get a high batting average. Okay. Now contrast that with the guys in the upper left-hand quarter. These are the guys who strike out a decent amount, but they compensate for that by basically getting hits and balls in play. Okay? So these are a very different kind of hitters, even though their batting average is similar to the batting averages in the first group. So now we're looking at guys like Joey Butler. You see Mike Trout is in that group, okay? Mike Trout's got a relatively high strikeout rate, but he tends to get balls, he gets hits when the ball's in play. Okay. Now, you might be asking at this point, so what? I mean, I've talked about decomposing a batting average in two things. I mean, why should it matter? I look at it this way. Well, it matters quite a bit because strikeout rates and hits and balls in play are very, very different from a luck skill perspective. What I mean by that is that you look at a bunch of strikeout rates, most of the differences you see are due to differences in abilities. There are their talents to not strike out. But if you look at balls hit in play, they tend to be more driven by luck. Now, I wanted to use, we had a very technical talk on this stuff yesterday with the guys from Stanford. I'm trying to be less technical here, so I'm trying to illustrate this idea. So here's my illustration. A group of coins. And now these are magical coins. These are not, I mean, obviously they're gold, but they're not, they're magical coins because every single coin's has a different probability of a head, okay? Now, maybe they're weighted differently or something, or they're unbalanced, but every single coin has a different probability of head. And what we're gonna do is we're gonna take a bunch of them and we're gonna toss them. Okay, we look at their performance, okay. So what you see here is, so I'm talking about a coin corresponds to a player, and just like the coin, a player will have a different probability of getting a hit, and we're going to flip the coins or look at the player's batting performance for like half a season. We're going to see a bunch of different success rates. Now, why are these success rates different? Well, there's two reasons. One reason is that the players have different abilities, or the coins have different probabilities. And the second reason is that there's this coin tossing variation. If you flip a coin 50 times, you're going to see a lot of variation in what can happen. So what we want to do is we basically want to separate out these two components. We want to find out how much is due to luck, or the coin tossing part, how much is due to the differences in abilities. That's what you get from a random effects model or a multi-level model. That's what the purpose is. Okay, so really that's the key thing, is we want to figure out how much is due to chance and how much is due to difference in the talents. Now, those two different things we talked about, the strikeout rate and the hits in play, are very different from this perspective. Strikeout rates are very much driven by ability. If you tell me someone's strikeout rate, it's going to be pretty consistent over his whole career. But if you tell me a guy's batting average and balls in play, I'll say, well, it's a little hard to tell. I mean, it's going to go up and down. You'll see a lot more fluctuation from season to season. Okay. So the idea of this paper is say, okay, what we'll do is we'll break down the batting average into, actually I broke into three components. You also can talk about home run rates. So you break it down by, first you take away strikeouts, then you take away home runs, and then you look at the remaining part. And what I did then is I looked at each group of rates, and I estimate them separately. Basically what I'm doing is I'm dividing the problem into three problems. And I'm estimating all the strikeout rates by using the same model, all the home run rates, and all the batting average and balls in play rates. And then I'm combining it all together to get a better estimate. Okay. So really it's a pretty simple idea. Once you understand there's a decomposition here, there's a natural way to do this. Okay, so now here's actually what I did. So this essentially, I showed you an early decomposition. This is actually a little more formal. And so you can represent a batting average as a function of a strikeout rate, a home run rate, and a batting average in balls in play. Now we're looking at only the plays that are inside the park. Okay, so here's an example what happens when you try this method. These are all the batting averages for the first half of the season. And what's remarkable is the variability. You see a lot of variability in their strikeout rates, which is the horizontal here. And you see a lot of variability in their batting average and balls in play rates. Okay. Now what I want to do is I want to predict their talents in these two components. And when you do this, you get this picture. So what you notice, if you compare this picture with this picture, you see that we're shrinking in the vertical dimension. The vertical dimension is the batting average and balls in play. We know those are very heavily chance driven, so you shrink them very strongly to the average. The strikeout rates, we don't shrink much because we believe those represent talents. So, okay, so if you look at this picture and you look at the guys on the right, which have low strikeout rates, I'm more confident those are really 300 batters. But the guys on the left, who are basically doing well because of batting average and balls in play, I'm less comfortable they're going to be a good hitter because they're going to be shrunk more toward the average. Now, Mike Trout's a bit unusual because Mike Trout, he hits the ball so hard that, he has this, there's a reason why he has a good batting average and balls in play because he hits the ball so hard. But as you know, there's a lot of luck in baseball. Okay, so, the question is this method any good? Well, I did a pretty thorough prediction. And what I did is I looked at one season, and I wanted to use the batting average for one season to predict the batting averages for the next season. And I looked at 50 seasons like this, pairs of seasons. And in each case, I got better predictions than the traditional shrinkage. Okay, so this is actually a better method. Now, I have to qualify that by saying that the size of the improvement is relatively small, but at least we're doing a better method here. Okay, so now I talked about batting average. You can do the same idea by looking at on-base percentages. You can decompose a on-base percentage essentially into a walk rate and a batting average. We already know we can decompose a batting average into three things. So the same method works fine. Fielding independent pitching measures. Okay, there is your basic definition. You can express that in terms of a strikeout rate, a home run rate, batting average and balls in play, and the walk rate. And you separately estimate the different components. You get better estimates of the talent here. This is the estimate. This is the statistic that you want to estimate the underlying ability. Okay, so really this is not the end of the story. This is really just the beginning of the story, because what this tells me is that I should focus more on the different components of batting average. I should not look at just simply batting average. And then so we know that focus more on strikeout rate, focus more on just looking at home run rate, and then batting average and balls in play. And now we can think what variables will affect these different components. Now, I've been influenced by this. It turns out there's a lot of talks here which are very relevant to this, and there's been a lot of talk about exit velocity. So last night, I had to download some exit velocity data, and so here's a graph. And I think we saw the same graph earlier today, like this. But I have a graph of exit velocity and batting average and balls in play, and there's a clear positive relationship, which tells me that I can explain a lot of the variation in batting average and balls in play by the exit velocity. Likewise, when you look at things like, again, strikeout rate, we want to know what factors influence strikeout rate. We're learning about things maybe in the brain, which controls reflexes. So maybe we can learn a lot more about strikeout rates by knowing about these two kind of measurements. So really, there's a lot of opportunities here. And of course, there's the issue of aging. I mean, how do we age? Do people who have low strikeout rates, do they age better than those who rely on home runs? Okay. I'm from Philadelphia, so I know about aging and Ryan Howard, so he's not aging particularly well. But then I don't think he's typical for his kind of player, I think. But anyway, so okay, so this paper appeared. Unfortunately, this journal is not open access. So if you want a copy of the paper, just ask me and I'll send you the copy of the paper. R code is available for all of these methods. All you got to do is Google that phrase and you can find my R code. And there's my email address if you have any questions about this. So, great. Yes?
Could you go back to the slide where you had your prediction?
Sure. Here. Yep.
No, I think it goes back a little further. What I'm trying to figure out is why, not on that particular equation, but on one of the others, it seemed like you were excluding home runs, which are hits.
Okay. Correct. Well, okay. I was trying to work with two dimensions first because that was easier. So this is just the introduction. Yeah. In my method, I basically considered three things. I first took away strikeouts, then I took away home runs, and then I looked at the remaining hits. So 3 components.
But the hits are home runs.
Correct. So in this graph, I'm just looking. Yeah, here I'm actually defining it. I'm a little not consistent here. That's including home runs here.
Right. So Trout and Cruz makes sense.
Correct. They're getting right. So that's why they look so good there. But yeah, so there's a reason why they're high. Other questions? People must be hungry now. But great. Okay, thank you very much.